Okay, so let's start. So first of all, welcome you guys to this course, Analog Circuits for Signal Processing. Okay, it's too right. Yeah. Visible, Latika? What I'm writing. Is it better? Huh? Okay, right. MC, right? Okay, great. Yeah, so this is first lecture. And as with the convention, let me first give a motivation to why you might want to learn this course. Whether it is just for the sake of like grades and getting your CPA, or is there some practical relevance to it? Right? And to answer that question, let me bring your attention to this picture. Oops. Sorry. Oops. Okay, so I hope some of you might recognize this. So what is this? So it's a very simplified block diagram for a RF radio receiver, right? If you don't recognize, it's okay. That's not the point of the course. But it is the best example one can give to motivate any circuit design course, because you kind of have several of them in your smartphones, smartwatches, laptops, and any IoT device, right? And uh, usually from the antenna, you receive this signal, and you first have what is known as a low noise amplifier. As the name suggests, it is supposed to amplify the signal while adding minimal amount of noise. And then comes the crucial part of the receiver chain, which is the mixing operation. And the job of this mixer is to take the incoming signal and down convert it in frequency. That is, translate it from the RF carrier to the baseband at DC. Right? For example, you might have a Bluetooth or Wi-Fi signal, say around 2.4 gigahertz. This might be the input of this mixer. And the job of the mixer is to down convert it so that you get the original signal around DC. And then you have a bunch of filters, amplifiers, and then an analog to digital converter. And later the digital samples are fed to a DSP that will do the further demodulation, right? And of course, we have all the courses in our group that covers different aspects of this receiver chain. For example, if you want to learn about how to generate or design good oscillators, we have circuits for frequency and phase synthesis course. And you learn about amplifiers, how to design them in 610 and 613. And you can learn about ADCs in the mixed signal course. But anyways, let's get back to this, and let's focus on this fellow. So this mixer, as you know, the job is to convert the signal in frequency from, say, a carrier frequency to DC, right? So in time domain, how do I model this operation? So I'm trying to translate a signal from some frequency, say I call it F0 to DC. So in time domain, if I have to model this, how do I model it? It's simply multiplication with a sinusoid, right? I hope that's clear. So this will be it. So this is the mixer. So the incoming signal ideally is multiplied by, say, cos 2 pi F0, right? And let's say this is my x of t and this is y of t. Can you tell me if this is a linear operation or a non-linear operation? So why did you say non-linear? Any reason? Oh, no. See, what does linearity mean? I mean, when do you say a system is linear? Superposition and homogeneity, right? So I give x1, the output I get is, say, x1 of t times this is cos whatever, right? If I give some another input x2, I'll get x2 of t times cos the same signal. So even if I have a linear combination of the inputs, say I give alpha 1 times x1 plus alpha 2 times x2, the output I'll get will be what? The input signal alpha 1 x1 plus alpha 2 x2 times the sine signal, right? And of course, this you can say it as alpha 1 times x1 times cos plus alpha 2 times x2 times cos, right? So you get back the same two outputs by the same scaling factor. So this is simply a linear operation, right? So then what's the next step? Is it time invariant or time variant? Huh? Okay, how many for time invariant? I mean, by that I mean raise your hands if you vote for time invariance. So how many for time variance? Okay, so you guys don't want to vote, huh? Not so so okay, come to some conclusion, right? Okay, let's look at it. So what does time invariance mean? If I give an input x of t, and if that produces an output y of t, if I delay the input by say t naught, or let me call it probably t1, the output must also be delayed by t1, right? So if I give an input x of t, what is the output I get? I'll have x of t times cos 2 pi f naught t. Okay. Now if I give an input x of t minus t1, what will be the output? T minus t1 times the same signal, right? Cos 2 pi f naught t. This is not okay. Let me probably say it. So this is the signal you get, right? But obviously this is not equal to y of t minus t1, right? Because what is y of t minus t1? It is x of t minus t1 times cos by f naught t minus t1, right? So obviously these two are not equal, right? So this is a time varying system, but is there some value of t1 for which this signal will equal this signal? Sorry? Yeah. So basically, if I choose t1 to be 1 over f naught or multiples of 1 over f naught, these two will be equal, right? Because cos is a periodic signal. So this is not simply a time varying system. There is some periodicity with which the system is time varying. Okay. So these kind of systems are called linear periodically time varying systems. So in short, it's called LPTV. Okay. Is that okay? So now in this receiver chain, even if you look at the ADC, I hope you have some understanding of what an analog to digital converter does. Basically, the operation consists of two parts. First, it has to sample the signal and then do a quantization, right? So basically, sampling, you can model it. How do I model sampling operation? Sorry? No, it's a switch, but mathematically, how do I model it? Sorry? Yeah, it's basically multiplication with a periodic impulse train. Is that fine? Right? So again, you have a similar scenario where the input seems to be multiplied by a periodic signal, right? So what kind of system is this? Again, it's LPTV, right? It's linear, periodically time varying. Is that clear? So even our ADC is an LPTV system. Okay, and not just these two blocks. There are several other blocks which are kind of not shown here for simplicity, which are LPTV systems in this receiver chain. Okay, for example, after the LNA, usually you might want to add a bandpass filter. Okay. And the reason you might want to add this bandpass filter is because, well, this might be your signal. Okay. let's say you are trying to receive a call, and let's say you are far away from the cell phone tower. So the strength of the signal you receive will be very, very small, less than minus 100 dBm, which is around few picowatts or less than few picowatts. Okay. So this picowatts of power is what you have to receive, right? But as you know, the RF spectrum is extremely crowded, probably more crowded than a Mumbai local train on Monday mornings, right? So what can happen is you may be trying to receive a call here, and you might be having a telephonic job interview, but nearby you'll have your friends chatting with their boyfriends or girlfriends, right? So they will be blasting out several watts of power because the signal that's coming out is directly from their mobile phones, and that will be several watts of power. And it's highly probable that those signals are also located very close to each other, right? So the job of your receiver is to only look at this small desired signal and reject all the other neighboring channels, right? So essentially you need a bandpass filter. And if you look at this bandpass filter, the center frequency is very high, right? For example, in this case, I have taken as 2.4 gigahertz, but the bandwidth of this filter probably might be few hundreds of kilohertz. Okay. And as it turns out, it is almost impossible to realize such a bandpass filter using LTI systems. And as we will see in the course, if we use LPTV systems, this is simply a cakewalk. Okay. And not just that, this filter should not have a fixed center frequency. As you know, every time you make a call, the center frequency will keep changing, right? So this bandpass filter must also be programmable, right? So as we'll see in the course, using LPTV systems, we can actually design very good programmable sharp bandpass filters with very small bandwidth. Okay. Sorry. Okay. So I guess that should convince you that LPTV systems are okay. One other LPTV system is this local oscillator itself, right? Because it's an oscillator, it produces an oscillatory waveform, which itself is periodic, right? So this is again a linear, periodically time varying system. Okay. So now that you are convinced that we have several useful and practically relevant LPTV systems, it only makes sense that we learn about them, right? And that will be the main objective of this course. Okay. And the rough outline will be this. So we'll look at a bunch of useful circuits. And of course, we'll derive them from first principles like switching regulator. We'll look at the technique of chopping. We'll see how to design the passive bandpass filters with this narrow, cutoff frequencies, and passive mixers. Okay, and what we'll see again that all these are all LPTV systems. So then we'll take a short detour. We'll learn about these LPTV systems in some detail, and we'll understand some interesting and very useful properties of these. And then using this understanding of LPTV systems, we'll look back at these circuits and see if we can improve them, improve these circuits better and analyze them better. Okay. Right. And of course, all of these circuits will be made using only ideal switches, R, L, and C, and probably some ideal op amps. Okay. So about the grading in the course for those who are crediting. So we'll have assignments, probably 3 or 4 of them. And of course, your mid-sem and end-sem. And as of now, all of them roughly have equal weightage, probably with a little more weightage for the assignments. Okay. But I'll let you know the final weightage later. Okay. And yeah, the slot, is on Wednesdays and Fridays between 12 to 1:15. Okay. So basically on these days, I am the one that is standing between you and your tasty food in your mess. Huh? Okay, cool. So let's first get started. And actually, before looking at switching regulators, first let's look at voltage references and what I'll call a linear regulator. So these will not be LPTV systems, but they'll help you understand and appreciate switching regulators better. Okay, so the first 2-3 classes I'll cover these, and in these classes we'll deal with MOSFETs at a very basic level. Okay, so even if some of you have not taken MOSFET, it's fine, as long as you know MOSFET is a device that produces a current whenever you apply a voltage at the gate. That should be good enough. Okay, so yeah, we have time. So let's start with voltage reference. And again, why do you need voltage reference? So I'll use my favorite picture here. So again, this is the RF receiver chain. So here, each of these blocks, amplifier, ADC, your processor, everything will require a supply voltage. Okay. And as you might be knowing, each of these blocks might be operating at different supply voltages. For example, your DSP or the digital processor, that will be at the cutting edge of the technology, and that might be running at say 0.7 or 0.8 volts. The rest of the analog modules can be running at say 1.2 volts or 1.8 or sometimes 2.5, right? So we have to generate all these supply voltages so that you can power your IC on chip. I mean IC on your phones. Okay. But you just have one single lithium-ion battery on your mobile phone, right? That probably is a 5-volt battery. And we might have to generate all of these voltages. See, I'll just give some numbers: 0.8, 1 volts, 0.8 volt. So we need to generate all of these voltages from this 5 volt. Makes sense, right? But the story does not end there. As you might be knowing, your battery in your cell phone will start to discharge quickly, right? So it will discharge from say 5 volt to probably 3 volt or less than that, depending on the battery. So if you just simply use this voltage to derive all of these, as the battery discharges, even these voltage will start to reduce, right? And of course, you don't want that, because your circuits will fail if the supply voltage falls below say 10% of the nominal value. Okay. So obviously, it does not make sense to simply rely on this battery. So we'll want a fixed voltage reference on the chip. Okay. And you will have to derive it from this battery. And this will make sure that even if the battery discharges, this voltage is fixed. Okay. So now using these two, you can generate all the required supply voltages. Make sense, right? So in other words, this fixed voltage reference must maintain its voltage constant irrespective of any changes in some other voltage or the current that is drawn, right? So if I have to plot the VI characteristics of this voltage reference, with x-axis as voltage and y-axis as current, how do you think this characteristic will look like? It's a vertical line, right? Is that fine? Voltage is constant irrespective of the current. So ideally, it should look like this. Not the straight line. Okay. This is a straight line. Okay. So this is the voltage, right? Some say V naught. Now, what is the element which has this kind of IV characteristics? an ideal voltage source, right? But as you might be knowing at this point of time, ideal voltage sources exist only on papers and textbooks, right? And on chip, we can't have an ideal voltage source because an ideal voltage source is an active device which can generate power, right? On the chip, we can only have passive devices, right, which can dissipate power. Okay. So if I have to use a passive device, how do you think the characteristic of that passive device will look like? Sorry. Yeah. So in which quadrants the characteristics will lie? Four. This is fourth, right? Correct. No, this is a passive device, right? But what happens if I reduce the voltage? I mean, make it less than zero. First and third quadrant. Okay. So I mean, for those who are not comfortable, let me just clarify that. So let's say you have any device, right? So this is the voltage across the device, and this is the current flowing through it, and this is the convention we follow, right? So what is the power dissipated? Sorry, V times I, right? Okay. So for a passive device, this power dissipated is always greater than zero. Okay. This is a sufficient condition for passivity, right? And for active device, if I take the VI product, what will it be? It will be less than zero, right? Because this will be delivering current, right? So VI product is less than zero for active elements. Okay. So now that this passive device must have VI product to be greater than zero, it makes sense that the characteristics must lie only in first and third quadrants. Okay, is that fine? So now can you help me sketch how the characteristics of this should look like? So I want this to be constant, but I cannot enter this quadrant, right? I cannot enter the fourth quadrant. So what will happen? Yeah, so ideally it should do something like this, right? And it has to pass through the origin, remember, right? And then it will do something. Okay. So this is an important thing for passive devices. It always must pass through origin, right? Because it can lie only in first and third quadrants. Okay. So now, is there some device that reminds you when you look at these characteristics which I have drawn in green? Diode, right? So if you use an ideal diode, this voltage will be roughly constant. And what is the voltage for silicon diodes? Yeah, probably 0.6 to 0.7. Okay. So how can I, sorry? Any questions? Please feel free to ask questions because it's a small classroom and we have a long lecture hour. So, I mean, if you miss something, it will be like you're watching some Korean movie without subtitles, no? So you'll be lost for the rest of the class. So please feel free to stop me. Okay. Okay. Yeah. So how do you generate this voltage using a diode now? Any suggestion? Huh? No, this is not a Zener diode, right? This is a regular diode. That's why I say the voltage is around 0.6 to 0.7. I mean, if I have to measure this voltage from a diode, what do I do? Sorry? Okay, we have a diode. What you are suggesting? Place a resistor here. No, but I mean, the diode is not on, right? It has to be forward biased. Okay. Yeah, this is a good suggestion. Okay, but again, looks like we need a voltage source, right? So, right, on chip we can get good current sources using MOSFETs. Okay. So, is there some other suggestion? I mean, even the fact that on the chip you can realize a decent current source. That's fine. I'll do this. if I pass a current I1, right? And if I measure this voltage, even if I increase the current I1, you know the VA characteristics of the diode, it will look something like this. So even if you increase the current a lot, say from here to here, the voltage variation is very small, right? So this is one way in which you can get a decent voltage reference, which is kind of roughly constant, right? Not completely constant, but more or less to the value, right? And as it turns out, in CMOS process, it is more easy to realize a TNP transistor than a simple diode for the following reason. So all the CMOS processes will have it on a P substrate, right? This is a P substrate. And what is the voltage to which, or the potential to which the P substrate is usually connected? Sorry? Yeah, it is lower, usually the lowest potential in a circuit, right? And usually it is ground, okay? That's usually the case. So now if you want to realize a PN junction, you might try to have an N well like this, okay? And you'll say, I mean, you'll try to realize a PN junction like this, right? But as you see, this P substrate is grounded, but that's not what you want, okay? So what you'll end up doing is you'll have one more P structure like this, and then realize a diode between these junctions. But as you can clearly see, you have a PNP transistor formed like this, right? So this is your P, N, and P, okay? So this is usually the case in CMOS process. It is kind of difficult to get an isolated diode, okay? You might, most of the time, you might end up getting a parasitic vertical bipolar transistor. So this diode, finally, when you implement it on chip, it will be like this bipolar transistor, and the P substrate is grounded. So the P substrate is basically what terminal for the for the BJT? Sorry, this is emitter, base collector, right? So this is grounded. So to realize a diode, what do I have to do? Sorry, base collector short circuit, right? I mean, you can see from here, right? So you have two diodes between emitter and base, and then one more diode between base and collector, right? And the collector is grounded. I just want one forward bias diode. So obviously I will short this to ground, right? So that the diode is inactive. Okay. So this is how we'll finally realize it on your chip. And I'll call this voltage as VEB to signify that it is between the emitter base junction. Okay. And I mean, but for the rest of the class, I will just draw this as a diode like this. Okay. Just for simplicity, that's all. Is that okay? Great. So this is our first attempt at generating a fixed voltage reference. And the idea was to pass a current through a forward bias diode, and you will get a constant voltage more or less, right? And as we saw, even if this voltage varies, I call VDD, this voltage is more or less constant, okay? So you have a constant reference voltage irrespective of any voltage variations in your circuit. But as it turns out, for a circuit designer, there are two other guys which kill you, and they are process and temperature variations. Okay, so these are the three enemies for a circuit designer. But having an enemy is not that bad because, as they say, enemies bring the best out of you. And if not for these variations, there is less job for us to do, right? Okay, so getting back to topic. So this is to some extent tackling voltage variations. Okay, but we have something called process variation. By this I mean that let's say you fabricate 100 ICs, it's not necessary that all of them have the same properties. For example, in this case, if you fabricate 100 diodes from your foundry, the voltages might be slightly different, 0.6, 0.61, 0.62, and so on, for the same current. Okay. And the second is, of course, the temperature variation, which I guess is straightforward. It's basically the variation in the voltage in the temperature changes. Okay. And usually this is called the PVT variation. Right. So now let's see how this voltage performs well with temperature. Right. So let's say if I try to plot this diode voltage versus temperature by keeping the current constant, what do you think? How do you think the curve will look like? Will it remain constant? Will it increase, decrease? Okay, let's sorry. Say it's okay. Increase or decrease? I mean, can do three things, right? Constant, increase, decrease, increase. Okay, we'll see. Okay, let's stop guessing and try to work it out to some extent. So if I pass a current through a forward bias diode, what is the voltage developed across the diode? Right, VT ln of. Is this okay? This equation is familiar, I guess. If not, this is the equation for a diode. Okay, and of course, this is not the exact. You will have +1 here, so this is an approximate relation. And what is VT? KT by Q, right? So this is KT by Q ln of I1 by IS. And what is IS here? This is a reverse saturation current, right? You can think of it as an intrinsic property for the diode, right? So now from this expression, can you tell me what might happen if I increase the temperature? It looks like it will increase. Right. So he has a point. Okay. See here, these two are constant by fundamental physics. This is fixed. This is electronic charge fixed. This is, we can make sure the current is constant. But as it turns out, this fellow, the reverse saturation current for the diode, is dependent on temperature, and approximately you can say that it follows this relation, which is I0 e power minus VBG by VT. Can't see VBG by VT, where VBG is the band gap voltage. Okay. And does anyone remember what is the band gap for a silicon at room temperature? Roughly 1.1. And of course, this I0 itself is dependent on temperature, but for simplicity and first order calculations, let's say we ignore that, right? So let me erase this probably. So now if I try to plug in this expression of IS in here, what do I get for VB? Can work out, right? It's not so big. Sorry? KT by Q ln. Great. Okay. Right. I mean, this is simple, right? This exponential goes into the ln and comes out, and this VT gets cancelled with this guy, and you'll have this expression. Is that okay? Yeah. So now let's try to find how this varies with temperature by taking the first derivative. If I take it, what do I get? I mean, remember, band gap is an intrinsic property. It doesn't vary with temperature to a first order. And again, I1 is a constant current. I0 for now, let us assume it's constant. So what do I get? right? I naught. Is that okay? So this I'll slightly tweak it and say it's like this. Okay. So I can write it as Vt by T times ln of I1 by I0. Okay. So from this, can you tell me what Vt ln I1 by I0 is? From this equation, which I am kind of highlighting here, can you tell me what is Vt ln In by I0, I1 by I0? It's basically VEB minus VBG, right? So I'll put it in the next page. So the first derivative is we had Vt ln I1 by I0 by T, and the numerator is basically VEB minus VBG. Okay. So let's say we take in at room temperature, let's say the diode's forward bias voltage is 0.65 volt and band gap is say 1.12 volt. At room temperature, T is 300 Kelvin. Can someone work out and tell me what this number turns out to be? What when you are doing long division, Shubham? Yeah, I mean, that is basically around 1.56 millivolt per Kelvin. Okay. So if I now with this understanding, if I plot the forward bias diode voltage versus temperature, how will it look like? Will it increase, decrease, or constant? It should decrease, right? And we know that the slope is approximately this guy. And again, these values depend on the forward bias voltage and stuff. So in practice, you can find that this can vary from minus 1.5 to minus 2 millivolt per Kelvin. Okay. And when you design, you always rely on simulation. You simulate it and see what the slope is, right? Okay, so this more or less might do something like this. Okay, but the actual curve is something like this. Okay, I mean we that's because this I naught here, where is it? This itself is a complicated function of temperature. So it is not a simple linear variation with temperature. It has some higher order polynomial relation. Okay, but to a first order for like for our class, we'll assume that it's constant. That is, it is a linear slope, and the slope is minus 1.56 millivolt per Kelvin. Right. Right. No, no. I1 by IS, right? The reverse saturation current is not. Ah, right. Yeah.
So I1 is constant. I0 is assumed constant. It's also constant. From here it is a positive slope.
Yeah. I mean, again, this band gap is not this one, right? In the sense, yeah, I understand your confusion, but I mean, this value, if you calculate, I mean, you were saying that this looks positive. That's your question, right? Exactly. I mean, it turns out that this value of I naught will be several orders of magnitude higher than I1. Okay. That, sorry? Exactly. So the argument inside the lawn will be less than 1, and that's why you get the negative slope. Is that clear? I mean, his question was, it looks like from here it's positive slope, right? It's increasing with temperature. But the catch is, this fellow is much less than 1, So if you take a natural log of a quantity that is much less than 1, you get a negative sign. So, okay. Great. So this kind of characteristic where the voltage reduces with temperature is often called as complementary to absolute temperature, or often known as CTAT. Okay, this is just a definition. Great. So to summarize what we have done so far, we try to generate a constant reference by passing a current through a forward bias diode. But we find that this VEB, I'll call it 1, is a CTAT voltage. That is, as you increase the temperature, the voltage reduces with temperature, right? So this is the characteristics you get. This temperature, this is voltage. But I want a voltage that is kind of constant with temperature. Okay. But this is what we want. This is what we have. So what do you suggest we can do to get a constant voltage with temperature? Not in terms of circuit, I mean just in words. Add some other voltage that increases with temperature, right? So if you generate some other voltage that increases with temperature, and if you make sure that the slopes of these two lines are exactly equal but with opposite signs, then when you add them, you will get a constant voltage, right? And this kind of voltage, which linearly increases with temperature, is called proportional to absolute temperature. Repeat that voltage. Is it okay? Cool. So now let's see how we can generate such a p-tat voltage. And for that, let's look at the diodes, I mean forward bias diode voltage expression. So it was VT ln I1 by IS. So here, initially we thought that this voltage might increase linearly with temperature because of this fellow VT, right? But we got the CTAT behavior because of IS, right? So if we can somehow get rid of IS in this expression, then it looks like we can generate a p-tat voltage, right? So what we want is VT ln I1 by IS, but something like I want to multiply it here, right? So that it gets cancelled. But of course, I can't leave it hanging like this. I should have one more current in the denominator. So let's say it's some other current I2. Okay. So let us say we generate those two currents I1 and I2, which can be kept roughly constant, right? So now what is this? If I expand it, what do I get? I1 by IS minus VT ln I2 by IS. Okay, is that fine? So let me probably take this guy to the next page. Right, so let's here. So how do we generate this voltage? Now we have two voltages and we have to take the difference, right? So how do I generate the first term here? We need to pass a current I1 through a diode, right? So I'll pass the current I1 through a diode. Okay. Now to generate this voltage, I'll pass another current I2 through one identical diode, right? That's important. So now if I take the difference between these two voltages, we will get the required one. And let me simplify this. What is this finally? VT ln. If I simplify it, what is the final expression? It's simply I1 by I2. Okay. So this I'll call as VPTAT to signify it is the PTAT voltage. Okay. Great. And let's say I2, instead of choosing random values for I1 and I2, usually it's easier to choose it like this. Say I2 is I1 by N, or I1 is some integer times I2, right? And if I do that, what is my PTAT expression? What is it? VT ln of N. Okay. Is that fine? Great. So here, let me probably redraw it here. So now we know the values of the currents. This is I1. And what is this current? I2 is I1 by N, right? That's what we are choosing. But again, another simplification we can do is, let's say I want to have the same currents. Okay. And again, this is again for practical purposes. It is easy to generate equal currents than to have fractions or multiples of it. So let us say I want to have the same current in the two branches. This is I1, and let's say I want this also to be I1. Okay. Now if I just connect one diode, the current flowing through the diode is I1, right? But I want the current flowing through that diode to be I1 by N. So what do you think we can do? Right? Yeah, area can be increased, or the simplest way to think is we can connect N of them in parallel, right? So if you put N of them in parallel, all of them will steal a fraction of the current. This is N diodes, right? Then the current flowing through each individual diode is I1 by N, right? So this is I1, and here it is I1 by N. Okay. So what we'll have to do, we'll take a current, pass it through a diode, and this is say a VEB1, and a VEB1, the diode voltage is what kind of voltage? CTAT or PTAT? It's a CTAT voltage, right? So this is I'll call as VCTAT. I'll pass the same current through N of them. I'll just mark it as 1 and N to signify that we have N in parallel. And this will be another VEB. I'll call VEB2. If I take the difference between them, I get the PTAT voltage, right? So VCTAT is one diode drop. PTAT is the difference between two diode drops. And in this case, what does it simplify to? PTAT voltage, VT ln of N, right? Is that fine? Okay, great. So now we have generated these two voltages. Now the next job is to add them in an appropriate manner so that the positive slope cancels the negative slope, right? That's the whole principle, right? So all we want is to generate an output voltage, which is sum of the CTAT plus say a scaled version of the PTAT. Okay. And our final goal is to make V out by dt to be equal to what? 0, right? We want 0 dependence on temperature. So if I differentiate the CTAT with temperature, what is the slope we get? We calculated, right? What was it? Plus minus 1.56 millivolt per Kelvin. Now Kp times the derivative of Ptat voltage with temperature. And from this, can you tell me what is the derivative? I mean, we need to differentiate the Ptat voltage with respect to temperature. So this is the expression for the Ptat, right? Vt ln n. So if I take the first derivative with respect to temperature, what do I get? K by Q. Again, I'll write K by Q as Vt by T, right? That's more easy to calculate. So Vt by T ln n. Okay. So from this, we can quickly calculate what is Kp times ln n. So Kp times ln n will be 1.56 millivolt per Kelvin times temperature by Vt, right? Again, if you plug in the values, you'll get this to be 18, roughly. Okay. And so this is our Kp ln n. So if we let me put it to the next page, our final output voltage is VEB1 plus Kp times the Ptat voltage. The Ptat voltage is Vt ln n. Okay. This is VEB1 plus we found the value for Kp ln n, which was 18. So it is simply 18 times the thermal voltage. And let's say you take 0.65 for this and 26 millivolt at room temperature. So what is the value you get? Okay, I'll write it directly. It comes out as 1.12 volt, right? Yeah, so this voltage reminds you of what? Band gap of the silicon, right? And do you think this is a coincidence or there is something fundamental behind it? Well, did we encounter the band gap voltage somewhere along this? Right? In the expression for VEB, where was it? Yeah, this is the thing, right? So, I mean, I'll give it as an assignment. We can actually derive from this that the final voltage you'll get will be equal to the band gap voltage. Okay. So, this is basically the band gap. And for this reason, this kind of circuits are called band gap references. Okay. What? Okay. See, again, this 1.12 is from what the values we took, right? Finally, for your diode, if the VEB is 0.6 volt, the slope, I mean, this again, the slope we assumed is 1.56 millivolt per Kelvin. It can be minus 2 millivolt per Kelvin. So the exact value might vary between, say, 1.1 to 1.2 volt. Okay. It all depends on the material property, the diode you have, and stuff. But the point is, whatever voltage you get, that's going to be constant to the first order. Sorry? Right. Correct. Yeah, I mean, it is not just because of the value. Even if you, I mean, without putting the numbers, you calculate, this will be equal to band gap. Of course, approximately equal to band gap. If you use the entire equation, you will have some other terms also. Okay. So just to summarize, what we have done so far is the following. We took a current, passed it through a forward bias diode, and we generate this voltage, which is a CTAT voltage, and we pass the same current through n identical diodes, and the difference between these two is a Ptat voltage, and we added them with the appropriate scaling factor to get the band gap voltage. right? So if you finally plot the voltage variation with temperature, so our PTAT varies linearly with temperature, right? The CTAT voltage to a first order, let's say, does something like this. And obviously these two will not have equal slopes. We need to add with the appropriate scaling factor, and if you do that, you will have a constant voltage, right? And again, this is a very basic calculation. In reality, the CTAT voltage, as I explained, will have a curvature like this, right? So if the CTAT has a curvature like this, the final voltage, how do you think it will look like versus temperature? It will have the same curvature here like this, right? Because we have only corrected for the linear portion here, right? This PTAT is correcting only for the linear slope, but you have higher order derivatives also that has not been corrected here. So that will show up like this. And if you want to cancel this also exactly, then you need to generate a PTAT voltage that will do something like this, right? So yeah, probably we'll stop here and we'll continue from the next class. Okay.